Hi everyone, welcome back to homework 2. Uh, in this video we're going to be doing part 2A, and this is explaining and coding the secant and Newton methods for finding the root of a scalar one-dimensional function. So we're going to be finding the root of a function using these two different methods. Now I think the best way to start this is to look at this secant method. So the secant method is an algorithm to find the root. And it's going to use a succession of roots in secant lines to approximate the root of a function. Now, it does tell us here the secant method can be thought of as finite difference approximation of Newton's method, which we'll look at later. However, the secant method predates the Newton's method by over 3,000 years, which it's really interesting, actually. So, actually, if I can pull this up real quick. The way this secant method works is we're going to start with an initial guess, x0, which will take this x value here, and we basically go to our function, get the function value at that x value, and then we have another initial guess, which is x1, and we're going to basically get the function value at that x value, and we're going to connect those two lines, so f of x0 and f of x1. We connect that with a straight line. Now we're going to take the root of this line, and this is going to be our x2. And what we're going to do is we're going to get the function value at that x2, so right here, and then we're going to basically draw a secant line between x2 and x1, or f of x2 and f of x1. So the line, it looks like this, and we extend it down until it crosses the axis. And then we have we get the root of that line here. And we basically do this again, and we just keep doing this. So x3, we get a value that is about down here somewhere, and we're going to connect it with our x2 line. So it looks something like this. And it crosses the axis here, and then we basically get the value, and we do it again. And we keep drawing these lines until eventually, in theory, it should converge on this point here, which is the root of our function. So, how are we going to code this into Python? So, I'm going to start by import numpy as np, and we're going to need to come up with a function. So define, we'll call it sec for secant, and first thing we're going to need is a function. So we'll give it function f. And if you remember from this here, we need two guesses. So our x0 guess and our x1 guess. And we'll just call that x0 and x1. Now, from the way I described it, the way the secant method works is it's going to basically iterate. And it's going to keep doing this, keep drawing secant lines between successive points until we eventually get close enough to our actual root. So we want to specify a maximum number of times this can run, because in the event that it maybe doesn't converge, we're going to be running this to infinity, maybe. We don't really want that, so I'm going to set max iterations to be 50. And then we also may want to set a tolerance, so in case we get close enough to our actual root before we hit 50 iterations, we can just cancel the looping. So I'll specify TOL or tolerance, and we'll call it 1 times 10 to the negative 10. We'll just call it that. So this will be our function, and the first thing we want to do is, let's look back here. So we want to get these function values at our initial guesses. So we'll call this f0, or sorry, f0 equals f of x0. And of course, we're going to have to specify a function f. We'll do that after we do this. F1 equals f of x1, same thing. Okay, and so now how are we going to get these lines connecting the points? Because now we need to connect these two points here. So if we look down here, the secant method is defined by the recurrence relation, and it gives us this right here. As can be seen from this formula, two initial values, x0 and x1, are required, and they should be chosen close to the desired root. So we already have those two initial guesses. We already coded those in. So now we need to translate this into Python. And what they give us here is instead of 0, 1, and 2, they give n, n minus 1, n minus 2. So the way we'll code this is instead of looking for xn, we're going to look for x2. And xn minus 1 is going to be x1, and xn minus 2 is going to be x0. So this is going to be x1 minus f1, x1 minus f1, and then multiplied by x1 minus x0 over f1 minus f0. X1 minus x0 over f1 minus f0. And that'll give us our x2. And then what we want is to find the function value at x2. So f2 equals f of x2. And then we want to return x2. We want to return that point that gives us, that we want to return the point that is our root. So what we want to do is we want to continue to loop this. So if I pull this back up, so this is going to be our first line. We get our new root. We get f of x2. So f2 is here. So now we want to draw a line between f2 and f1. So the way we will do this is we want to set our x1 to be our new x0. And we want to set our x2 to be our new x1 in order to continue looping this. And then we can have f0 equals f of x0 because we want to change these values to the new ones. We have f1 equals f of x1, and then we want to loop it again. Now actually the way I have this written right now, this will not loop. So I'm going to move this down. And I want to say remember we have max iterations is 50, so we want to do this 50 times. So for I in range max iter, we want to put all of that in a loop. And then we want to involve this tolerance here. So what we want to see is if our value doesn't change by the tolerance, then we want to basically stop doing calculations. So if the value of f2 is less than max iter, we'll just break. And if not, it will keep going. And I might want this to be absolute value of f2. I think that might work out better, especially if we have if we're getting negative answers. Oh, here we go. Almost messed up there. we want this to be less than tolerance, not max it. Max it is 50. It'll basically break on the first loop. Okay, then we return x2. We'll run that, it runs fine. I actually want to define the function f, and this function f is going to take in x, basically our f of x here, return. I'm going to write out a function here. We'll call it x plus 0.3 times x minus 0.2 times x plus 0.1. And this makes it really easy to see where our roots should be. So our roots should be negative 0.3, positive 0.2, negative 0.1. Okay, and now I'm going to basically run this function, secant with f. And then we want initial guesses. So I'll put initial guesses. We'll say our first initial guess is, I don't know, we'll just do negative 0.1. And we'll say our second initial guess, x1 equals 0. We'll just do that. See what we get here. Okay, and we actually get negative 0.1. And that is one of our roots, because up here the specified the function we wrote, a root should be negative 0.1. We get negative 0.1. That's exactly what we're looking for. And it returned to us a root of our function. So a limitation of the secant method we should keep in mind here is that this is only going to return one root. And if we look up here, we obviously have 3 roots of this function. We only get 1 root returned. There may be some ways to get the other ones, maybe not with the secant method. It might be possible with different initial guesses, but we know that the secant method works and can for sure give us a root. So moving on, the next thing we want to look at is Newton's method for finding the root. Now Newton's method is a little bit different, and you can see right here we have our x1 equals x0 minus f of x0 divided by the derivative of f at x0. So this actually takes into account the derivative of the function. Let me see if I can find, okay, here we go. So the way that this works is that we take our initial guess here, we get the function value, and then we find the derivative of the function at that value. So that's this red line. We find where the red line crosses the x-axis, and then that's our new xn. So then we find the function value at that x point. So right here, we draw a derivative at that point, and we find where it intersects the x-axis. And we keep doing that until we eventually, it should converge to the root. Oh, it looks like there's a animation here. So we find the point, do the derivative, find where it crosses, get the new point down here, draw the derivative, find where it crosses the axis, get a new point, draw the line, crosses, and this is about the actual root. So this took about 5 steps to do. And this is basically what we're going to be coding. So again, this is just, we're basically just iterating, doing the same thing over and over again until eventually it should converge on our root. And of course, this is the equation. We basically are going to be using this in Python for Newton's method. So we'll go down here, we'll define, we'll just call it new. And we're going to need f, we're going to need an initial guess. And in this case, we actually only need 1 initial guess instead of 2 like before. We're going to use max iterations is 50. Tolerance is 1 times 10 to the negative 10. So first thing we need to do is find the function value at that x value, at that initial guess. So we'll say f0 equals f of x0. And then we need to get the derivative of that at that point too. So we can call it f prime. I guess, yeah, I guess I can't really do f apostrophe. Unless I can. Nah. We'll just call it fp for f prime. And we're going to need to get the derivative somehow. And I think the way I'm going to do this is I'm going to import Jax. So import Jax. And then import Jax.numpy as jnp. And this should give us access to Jax.grad. And this should give us the gradient. This should give us the gradient of our function, or the derivative of our function. And I actually went over gradient in homework 1, so I guess I already have a video going over what the gradient is. So it'll be the gradient of f. So that's fp, f. Okay, that should be what we're looking for. And then we basically want to do this. I'm just going to copy and paste this. So for I in range, max iterations, of course this is going to be different. Instead of this, we're going to have x1 equals, let me pull this up real quick, x1 equals x0 minus f0 over f prime at x0 equals x0 minus f0 divided by fp. I believe that should work. And then we want to get f1 equals f of x1. We're going to keep this here. We're going to change that to f1. We want to keep the same tolerance. Delete this, delete this. And then we want to return x1. That should be our answer. That should be our root. So I basically just coded this equation and told it to loop it on Python. Let's look at this real quick. Hopefully this runs. Okay. I'm just going to go ahead and shift in everything here. Okay. So we'll call a function, new f equals f, and we'll have x0 equals, and if we remember, we'll just say 0. That's pretty close to our, let's see, what is the issue here? Float. Maybe this needs a period. No. Let's see. Max iter. Yeah, I don't know if this. I don't know if this needs x0 equals x1. What is the issue here? New. Maybe we can say, instead of that, we can just say 0.1. No, it still doesn't like it. For I range max here. Maybe it's this. Do I need, like, x0 here? No. Interesting why it's not working. For I in range max iter f0 over f prime at x0, absolute value of f1 is less than tolerance break, x naught or x0 equals x1, f0 equals f of x0, return x1. What is... Float object not be interpreted as an integer. Maybe that's the issue? I don't know why that would be the issue. Oh, I am not exactly sure what the issue is. Because I added this, and it wasn't working, and then I added this, and I'm not sure if I fixed it in the meantime, but then I removed it again, and now it works. Okay, so it gives us 0.2 as our answer. And if we look up here, a root of this is 0.2. So that is correct. This gave us the correct answer. Okay. Yeah. 0.2. Again, this method only gives us one. This method only gives us one root. When there are technically 3 roots here, we may be able to get the other roots using a different initial guess, possibly. But yeah, so the secant method and the Newton method, both coded in Python, and they're able to find a root of a scalar one-dimensional function. So thank you for watching, and I will see you in part 2b.